In this session, we are going to deal with assembly language programming, right? And here we are going to see how to write a small program for addition of two numbers using ARM instruction set. So first of all, we will see memory map of LPC2148. Memory map means this shows the whole memory area of LPC2148. Why we are going to see this memory area before starting the program? Because you should have a clear understanding where you are going to store the program as well as where you are going to store the data in this microcontroller, right? So it is having total 4 GB memory space and it is divided into different sections or different areas. And here you can see that from address location 000 to 7FFF, you can see that it is written on chip non-volatile memory, right? That means from 000 to 7FFF, it is used for storing program. Why? Because it is a non-volatile memory. Once you are storing the program, even though power is not there, it should not get erased. That is why you are going to store the program in this non-volatile memory. The type of code memory you are having is flash ROM, right? So it is the latest type of read-only memory. So flash memory means you can see it in most of your pen drives. You are having flash memory. What is the advantage of flash memory? Bulk read and write is possible. You can write bulk data as well as read bulk data from this flash ROM. That is the advantage of using flash memory. And another advantage is that it can be easily read and written with the help of a normal VCC supply. It can be easily read and written, and within a fraction of a second you can write this, right? Because in the older memory like EPROM and other memory, it will take more time, but here in a fraction of a second you can write it. And the last advantage is that it is having 1 lakh erase cycles. That means you can read and write, or write basically 1 lakh times program into this, right? That is a flash memory. Then from 4000 to 4007FFF, you are having on chip static RAM. So this area is used for storing the data. So this is known as the data memory. And RAM, you already know, it is a volatile memory. So once the power is not there, the data will get erased, right? So this area is used for storing data and this area is used for storing program, right? So from 000 to 7FF, it is used for storing program, and that area is known as code memory, right? Similarly, from 4000 to 4007FFF, this area is used for storing data. So this area is known as data memory, right? So this is the area where you are writing program. This is the area where you are writing program. This understanding you should have before you start assembly language programming, where you are storing the program, where you are storing the data. Next, we will see how to write a small program for adding two numbers. So whatever arithmetic or logical operation you are performing, that will be done in a unit known as arithmetic and logical unit. So this is arithmetic and logic unit present in ARM, and this arithmetic and logic unit or ALU is having two inputs. One is known as RN. So RN stands for the first operand register, that is a register which is holding the first data. Second one is known as RM. It is a register holding the second operand, right? Or this is a register holding the second data. And you can see there is a block known as barrel shifter which is connected to the second operand. The barrel shifter is a block which is used for performing multiple number of shifts to a second data in a single cycle. Multiple number of shifts you can perform on a single data or a second data. It is available only in the second data in a single cycle itself. So barrel shifter we have already seen. So that is the use of barrel shifter. So let us take, I am going to use Rn as the first operand, Rm as the second operand. And for time being, I am going to use Rn as R1. So R1 is my first operand, right? So ALU will get the first operand from R1 register. Similarly, ALU will get second operand from R2 register. Right? Now for time being I am not using barrel shifter, directly I am giving to ALU. Right? And the arithmetic operation, in my case addition, I am going to add content of R1 and R2. So where will be the addition performed? In the ALU. And after performing addition of R1 and R2, result I am going to store in a register known as RD. RD stands for destination register. In my case, I am using R0 as the destination register. So R1 is my first operand register, R2 is my second operand register, and R0 is my destination register. Right? So now I am going to give two operands to this register. Let us take I am going to give my first operand 1 to R1. So I am going to move hexadecimal 1 to R1. Right? Similarly, I am going to move a second data, that is hexadecimal 2 to R2. So I am having 1 in R1, 2 in R2. And addition will be performed and result 3 will be stored onto R0. So this is operation. 1 will be moved to R1, 2 will be moved to R2. Then addition will be performed, result will be stored in R0. Right. So what is the first step? You need to move first data, that is 1 to R1. How will you move 1 to R1? How will you write a instruction for that? Move R1 comma hash 1. Hash 1 means it is an immediate data. So when I am writing move R1 comma hash 1, hexadecimal 1 or 1, you are moving to R1. Right. Then similarly, how will I move 2 to R2? I am writing move R2 comma hash 2. So the immediate data 2 will be moved to R2. So 1 is there in R1, 2 is there in R2. What is the next step? You need to add these two. How will you add? Add 3 operands are there. R0 comma R1 comma R2. R0 will be destination, R1 will be first operand, R2 will be second operand. So content of R1, that is 1, and content of R2, that is 2. So 1 and 2 will be added together. Result 3 will be taken to R0. Right. So these are the 3 instructions required for adding two numbers. But for making it into a program, few more steps are required. Right. When you are writing a C program, you will be adding hash include, void main, etc. Those steps you will be adding. So like that, few steps are needed to be written here also in order to make it into a complete program. Right. So the first step you need to add is known as area. So area is nothing but an assembler directive. So what do you mean by an assembler directive? Assembler directive is a directive which gives directions to the assembler. What is assembler? Assembler will convert assembly language program into machine language program. Right. So area is an assembler directive. So what do you mean by an assembler directive? Assembler directive gives directions to the assembler itself. So assembler directive cannot be executed by an assembler. Assembler cannot execute an assembler directive. Why? Because assembler directive itself gives directions to the assembler what to do. So area assembler directive instructs or gives direction to the assembler that, or area tells the assembler that this area should be used for storing the program. Whatever program you are writing here should be stored in a particular area. So in the previous slide we have seen two areas. One is known as code memory, another one is known as data memory. So in my case I am going to instruct the assembler that you store my program in the code memory. Store my program in code memory. How will I instruct that? Using this directive known as area. So area is having 3 parameters. First parameter is known as the name what you are going to give to this program. So for time being I am giving the name as addition. Whatever name you need to give for the program, you can give it here. Whatever name you need, you can give it here. This is a name of the program. That is the first parameter. Second parameter is the actual area where you are going to store this program. So I told in my case I need to store the program in code memory, right? So the second parameter is actually specifies which area you need to store. So I am writing it as code. This code keyword you cannot change, and it should be in capitals also. So this is the keyword showing that you are going to store the program in code memory. So you can change the first parameter because it is user defined, but the second parameter should be code or data, etc. You cannot change it. For time being, I am going to store the program in code memory. So the second parameter should be code, C-O-D-E in capital. So this shows that I am going to store the program in code memory. Third parameter is the attribute. What operation you are going to do. This attribute can be either read only or read write. In my case, I am going to write this program with an attribute read only. So this keyword also you cannot change. Either you should write it read only or read write. In my case, I am going to make this program as read only. So I am using the attribute as read only. So area directive gives the direction to the assembler that you should store this program in code memory, and that memory should be of type read only. You can only read from that, and this is the name of the program, right? Then you should use another assembler directive known as entry. So entry assembler directive instructs the assembler that this is the starting point of the program. From this line onwards, I am going to write my program. So entry assembler directives instruct the assembler that this is the starting of the program. Finally, when you are finishing the program, you should write another directive known as end. So end is another assembler directive which instructs the assembler that this is the physical end of the program, right? So this is the physical end of the program. So whatever you are writing after this end will be discarded by the assembler. Whatever you are writing after end will be discarded by the assembler. So area, entry and end, these three are known as assembler directives which gives directions to the assembler, right? So almost the framework of the program is done. Few more things has to be done. So before that, let us see the program memory or code memory. This is a code memory. So how you are going to write the program in the code memory? Code memory is used for storing the program. How it is done? In the let us take this is a code memory or program memory. It is starting from 000 to, we have seen in the last side we have seen 000 onwards it is starting. So in 000 you are writing the first instruction. What is my first instruction? Move r1 comma #1. So the first instruction will be stored in 0th location of code memory or program memory. Second instruction will be stored in next location. And what is the address of the next location? Each memory location will have its own corresponding address. What is the location of next address? It is not 01, it is 04. Why it is 04? In the previous class I have told that whatever instruction you are writing, that will be decoded into 32-bit opcode. Whatever instruction you are writing, that instruction will be decoded into 32-bit opcode in the case of ARM microprocessor. So if I am writing move r1 comma #1, it will be converted into 32-bit opcode. What opcode you are getting for each instruction we will be seeing in the forthcoming classes. So now you understand that whatever instruction you are writing, it will be converted into 32-bit opcode. And that opcode, by executing that, because that opcode only can be understood by the processor. If I am writing move r1 comma #1, processor cannot understand anything. This should be converted into 32-bit opcode, and based on that opcode only the processor is executing the instruction, right? So since I want to store 32-bit opcode, how will I store it? It will be splitted up into 4 8-bits data, right? Because in ARM your memory is byte addressable. What does it mean? In each location you can store only 1 byte of instruction or data, right? So in ARM your memory is byte addressable, That means your whole memory is divided into bytes. One location can store only 1 byte. So in the location with an address 0000, you can store only LSB 1 byte. The second byte will be, so if you want to store 32 bits, how many bytes are required? Total how many bytes are required? 4 bytes are required. Right. Each byte can store 8 bits. So since you want to store 32 bits, 4 bytes are required. So 4 locations are required for storing a 32-bit instruction. So in the first location you are having address 000. In the first location you will be storing the first byte of this instruction. In the second location, what will be second location? Address will be 0001. In the second location, we will be storing the second byte of this instruction. In the third location, what will be third location? 02. In the third location, we will be storing the third byte of this instruction. And fourth location will be 03. So in the fourth location with the address 03, we will be storing the fourth byte of the same instruction. So for storing this 32-bit instruction, 4 bytes are required. For storing each byte, each location is required. So for storing this 32 bits, total 4 bytes locations are required. So 0, 0, 0, 1, 0, 2, 0, 3. These 4 locations are used for storing the 4 bytes of this instruction or 32 bits of this instruction. So where will be the next instruction stored? From 04 onwards. So 04, 05, 06, 07. 04, 05, 06, 07. These 4 locations or these 4 bytes are used for storing the next instruction. Similarly, where will be the third instruction stored? From 8 onwards. Because from 4, 5, 6, 7, you will be storing this. From 8 onwards, that is 08, 09, then A, B, because it is hexadecimal representation. 08, 09, A and B. In this 4 location, you will be storing add the third instruction. So like this you are storing the third instruction. So where will be the next instruction stored? In 0C, because 08, 89 AB you will be storing add. From C onwards next instruction will be stored. But in our case, from next location onwards we are not having any instruction because only 3 lines are there, 3 instructions are there. So what will happen? What will happen to the processor? In the case of an embedded system, the processor will start executing the code from the starting location 00. Then it will keep on incrementing the program counter, or it will keep on incrementing location by location, and whatever instruction you have written there will be executed by the processor. Right? Like that it will keep on incrementing the program counter, and when it is reaching the end of the program memory, it will again go back to 00. Right. So whatever an embedded system program you are writing, that program will be infinitely executed. But in the case of a normal C program, if you are writing a program to display hello world, how many times a program will execute in C? Normal C program? Yes, only once. Whatever C program you are writing, it will be executed only once by default. But in the case of an embedded system program, it is not like that way. If you are writing a program, that program will be infinitely executed. That is why in the case of a mobile phone, whenever you are pressing the unlock button, it is getting unlocked. That means a code which is keeping track of this button press is running behind the scene or in the background. That is why whenever you are pressing the button, it is getting activated and it is coming out of sleep. Right. So whatever embedded system you are having, the program will be executed infinitely. How it is getting executed? Will start executing from the 00. It will go on continuing till the end. Again it will go back to the first location. Like that it will be executing. But here in my case, after 08 I am not having any instruction. So when the program counter is pointing here, in the next instruction, this will be executed. This will executed. After executing this, this location will be executed, that is 0x. 0C will start executing. But here you are not having a program. So since when the processor see that there is no program in the particular location, what will happen? Prefetch abort will happen. Processor will move on to abort mode of operation and the normal execution will be stopped. It will be in a abort mode of operation, but because it cannot see any instruction here. So in order to avoid that, what you should write? You should not allow the processor to go to a location where program statement or instruction is not written. You should not allow the program counter to move to a location where there is no program. Right. So what you should do? You should tell the processor to go to the same instruction again and again. So it is something like an infinite loop. How will you do that? You will be using an instruction known as branch instruction, that is B. So if I am writing an instruction B this address, so what will happen? It will branch from this location, that is 0C, to that location itself, right? So you will be branching from this location to this location itself. So it is something like an infinite loop, right? So when it is getting when the program counter is coming to see the next instruction cycle, this instruction will be executed. What is this instruction? Go to this instruction itself, go to this location itself. So it is something like a while one loop or an infinite loop, right? How many ever times you are keep on executing the program counter will be standing here, and this instruction will be keep on executing. So by doing this, what you are achieving? You are not allowing the processor to go to the next line where there is no program, right? So since the embedded system program will be infinitely running, you will keep on executing this line infinitely. And there is one more use for this. This will allow us to execute the previous program whatever you have written here only once, because when you are adding 1 and 2 you should get 3. You should not again add some other numbers to it and keep on incrementing. I should get the result as 3. So for getting 3, these 3 statements should be executed only once, right? If you are not writing the statement, at some point of time these statements will be again executed after some time. That should not happen, right? So by using this branch statement, you are achieving two things. You are not allowing the processor to go to the next location where instruction is not there. That means you are not allowing the processor to go to prefetch abort mode. And the second advantage is that by writing this infinite loop, you are allowing our program to execute only once, so that I will be getting a deterministic result. When I am adding 1 and 2, I should get 3. If I am keep on adding this, result will keep on changing. So by using this branch, you are avoiding that, so that your program will be executed only once, right? And here, so this is known, and we are giving a name for this infinite jump to the same location, that is known as short jump. Since you are jumping or branching to the same location again and again, we are calling it as short jump. And when we are writing a program, it will be difficult for us to find which address you have written this branch statement. Since this program is very small, you can manually calculate in 00C you are having this branch. So branch, you should branch to same location itself. So the same address you will give here. But when you are writing bigger program, I will not be able to identify which address I need to jump to in order to have a short jump. So what will I do? In order to avoid that, instead of using this address, I can use a name for that. That is known as label. So in the actual program, I will not write B and the actual address. Instead of address, I will write something known as label or a name. So in the actual program, what I will write? I will be writing B, that is branch, and my label is stop, right? And before writing the instruction, I will add that label here. So stop, B stop, what does it mean? When the processor is executing this, it will branch to a location where you have given a label as stop. So it will branch to this location itself infinitely. So instead of giving this address, you are using a label stop. So when the assembler is assembling this program, what will happen? Automatically this label or stop label will be replaced with the corresponding address. So while you are assembling the program, the assembler will automatically replace this label with the corresponding address, so that your actual program will be 00C B000C. This label will be automatically replaced with the actual address at the time of assembly. So this is how you are writing a basic assembly language program. We will see the steps one more time. First step is you are writing area. Area defines in which location you should write the program. In my case, I am going to write the program in code memory area. So I am specifying it as code memory, and the attribute is it is of type read only. Then the first parameter shows the name of the program. Whatever name you need, you can give here. Then the second step is entry. Entry assembler directive tells that this is the starting of the program. From here onwards, you are starting the program. Then you are writing move R1 comma #1. That means immediate data 1 you are moving to R1. Then similarly you are moving 2 to R2. Then you are adding R1 and R2, result you are storing back to R0. Now after writing all the statements, you are writing a short jump, right? So that the processor will not go to a location where program is not there, and by using this you are allowing this program to execute only once, that is stop, B stop, and the last one end shows the physical end of the program. Right? So this is how we are writing a small basic addition program using ARM assembly language program.